Think of any whole number you can imagine, no matter how large or small. The moment you pick it, it instantly falls into one of two distinct camps. It splits right down the middle into either even or odd. On one side, we have the evens, the steady, reliable sequence of 2, 4, 6, and 8. On the other, the odds, the alternating steps of 1, 3, 5, and 7. But why does this specific split exist? How does separating numbers into just two categories dictate the underlying rules of how they interact? This binary code dictates mathematical behavior long before you ever perform a calculation. It is a structural rule that exists at the foundation of every operation. To read this code, we look at the physical mechanics of division. If you take a quantity, divide it by 2, and the pieces snap into perfect pairs, it is even. If you have one lone piece that refuses to pair up, a remainder of 1, it is odd. Now, you don't actually have to map out a billion dots to check for a remainder. Our base 10 number system gives us a built-in shortcut. You only need to look at the very last digit. If a number ends in 0, 2, 4, 6, or 8, it will always divide cleanly into pairs. If it ends in 1, 3, 5, 7, or 9, it will always leave that single remainder behind. Because the final digit perfectly mirrors the remainder of the entire value, you can identify the parity of any integer instantly, no matter how many digits it contains. This rule of parity applies identically to negative integers. The same pairing logic works for -2, -4, and -100 as it does for their positive counterparts. But right in the middle of that timeline sits the number 0, and 0 often sparks a debate. Is nothing even, odd, or neither? The math gives us a definitive answer. If you take 0 and divide it by 2, the result is 0, with a remainder of 0. Because there is no leftover piece of 1, 0 is an even number. The law of perfect pairs remains constant across the entire number line. There are no exceptions, even for the concept of nothingness. To predict how numbers will behave in every possible scenario, mathematicians translate this physical pattern into algebra. This workbook defines an even number algebraically. If an expression factors into a clean multiple of 2, written as 2n, it is even. An odd number is that exact same even multiple plus or minus a remainder of 1, written 2n plus or minus 1. In both of these equations, the letter n represents any whole integer. By converting parity into these two simple formulas, mathematicians can prove the outcome of any arithmetic interaction. When you add or multiply two numbers, you are essentially watching their underlying parity codes interact. Take the first rule of addition. As this equation shows, adding an even number to another even number results in an expression that still contains a factor of 2. Even plus even always equals even. Adding two odd numbers results in an even number. Their two isolated remainders lock together, forming a perfect pair. But adding an even and an odd number stays odd. The single remainder has nothing to pair up with, remaining unresolved. Multiplication has its own set of rigid rules. If you multiply an even number by any other whole number, the product will always be even. The only way to get an odd product is to multiply an odd number by another odd number. These arithmetic results are not random. They are fixed outcomes dictated by how these two parity codes interact. Look at 18, 27, and 104. Thanks to the final digit, you instantly see 18 and 104 are even, while 27 is odd. Now check the extremes. 999, 0, and -12. The rule holds. 999 is odd, while 0 and -12 are even. The scale or sign of the number is irrelevant. The code of parity operates instantly across the entire number system. This binary split appears in patterns across higher mathematics. Parity reveals predictable sequences in geometry, forms the foundation for binary computer logic, and helps structure the complexities of number theory. Can every whole number really be understood simply by whether it forms a perfect pair? These two simple categories provide a constant framework for navigating the number system, ensuring that even in the most complex equations, the rules of the pair never change.